Formal charge. See, Lewis dot structure in general do not represent the actual shape of the molecules. Suppose in case of the polyatomic ions, the net charges possessed by the ions as a whole and not by a particular atom. See, it is however the feasible to assign a formal charge on each atom. So, the formal charge of an atom in a polyatomic molecule or ion may be defined as the difference between the number of valence electron of that atom in an isolated or free state and the number of the electrons are assigned to that atom in the Lewis structure. See, simply we can express that formal charge is equal to total number of valence electron in free atom, total number of valence electrons in free atom minus total number of, that is non-bonding lone pair of electrons, that is lone pair of electrons minus half into then bonding pair, that is shared electrons. So this is the formula, or simply we can write it formal charge is equal to, that's mean is the charge is that is the charge is assigned to an atom in a molecule, that is formal charge is equal to, you can write it, that is number of valence electron minus number of dots minus number of lines. So for example, if I take O3 molecule, the Lewis dot structure will be like this. So the Lewis dot structure like this. See, just make a mark for the oxygen numbers like this. The first oxygen, and this is the second oxygen, and this is the third oxygen. Now we can calculate the formal charge of the compound, the O3 molecule. So this is a polyatomic molecule. So here the formula is what? FC means formal charge. That's number of valence electron minus number of dots minus number of lines. So here take a first oxygen, that is formal charge on oxygen 1, that is this oxygen. Now the formula is what? Number of valence electron. Number of valence electron for this is oxygen belongs to 6 group, so that valence electron is 6. Then number of dots minus that number of dots. Here how many dots are there? 2 dots are there, so number of dots is 2. Then minus number of lines. How many lines are joined here? 1, 2, 3. So 3 lines. So 6 minus 5, so it's plus 1. So this first oxygen having plus charge, plus 1. Then second formal charge on the second oxygen, oxygen number 2. This is first and this is 2. Here 2 oxygen, formal charge is what? Valence electron is what? 6 for this oxygen, and the number of dots is how many dots? 4. So minus 4. Then the number of lines 1, 2. So number of lines 2. So 6 minus 6, it will become 0. Then oxygen number 3. This formal charge on oxygen 3. Oxygen number 3. Look at here. Valence electron 6 and the number of dots, 6 dots are there, and number of lines 1. So minus 1. So here this oxygen having the minus 1 charge. So that simply we can write it, this having the minus and this having the plus charge, right? So this is the O3 molecule, formal charge for the O3 molecule. So minus plus 1 for the first carbon, second carbon 0, then third carbon is minus, not carbon, oxygen. The first oxygen is 0, second oxygen is first oxygen plus 1, second oxygen is 0, third oxygen is minus 1. Okay. Limitation of octet rule. The octet rule usually, though useful, it is not universal. It's quite useful for the understanding the structures of most of the organic compounds, and it applies mainly to the second period elements of the periodic table. So here there are three types of exceptions to the octet rule. That is, one is the incomplete octet of the central atom. Second is odd electron molecule. First one is the incomplete octet of central atom. Second one is odd electron molecule. Odd electron molecule. Third one is expanded octet. So these three types. First we will see the incomplete octet of the central atom. Some compounds, like the number of electrons surrounding the central atom is less than the 8. So this is especially the case of the elements having less than 4 valence electron. Like example, lithium chloride, that is beryllium hydride, and boron trichloride. See here, the lithium chloride we can write like this. Then the beryllium hydride. So beryllium hydride, this is 2. Beryllium hydride. So beryllium hydride like this. The structure like this. Then boron trichloride. So Cl, Cl, Cl. So this is the incomplete octet of the central atom. That is lithium, beryllium, and boron have, that is this 1, this 2, and this 3, the valence electron only. So similarly, some other such compounds are aluminum chloride, then boron trifluoride, like this. Then next is the odd electron molecule. Second is the odd electron molecule. In molecule with an odd number of electron, like nitric oxide, that's NO, nitric oxide, and the nitrogen dioxide, like this, that is NO2, NO and NO2. The octet rule is not satisfied for the all atoms. Look at here, nitrogen, the monoxide, that is nitrogen oxide. Here the Lewis dot structure like this. Then similarly for NO2, the structure only one electron and plus charge, like this. Here this having, see, the odd electron numbers like this. Then look at here, this is the odd electron, one electron. Okay. In elements, that is expanded, third is expanded octet, that is in elements in and beyond the third period of the periodic table have, apart from 3s and 3p, that is 3s and 3p orbitals, the 3d orbitals also available for bonding. So in a number of compounds of these elements, there are more than 8 valence electrons around the central atom. So this is called expanded octet. That is, obviously the octet rule does not apply in such cases. Some of the examples such compounds are like PF5, SF6, phosphorus pentafluoride, sulfur hexafluoride, like the sulfuric acid, H2SO4. So this that is in the number of coordination compounds. We can write it here. Look at here, for PF5, 10 electrons, that is phosphorus, there is 10 electrons around the phosphorus atom. 1, 2, 3, 4, 5. So 10 electrons are around. Here in sulfur SF6, 12 electrons are here. 1, 2, 3, 4, 5, 6. So that 12 electrons are surrounded here. In the sulfuric acid, here also 2, 4, 8, 10, 12. So 12 electrons are surrounded here. Here also 12 electron, and here also 12 electron. Here 10 electrons are surrounded here. Here does not fit into this octet configuration. Okay. Then the other drawback of the octet theory means it is clear that the octet rule is based upon the chemical inertness of the noble gases. However, some noble gases also combine with oxygen and fluorine to form the number of compounds like xenon difluoride, then krypton difluoride, xenon oxyfluoride compounds like this. Then this theory does not account for the shape of the molecule, and it does not explain the relative stability of the molecules being totally silent about the energy of a molecule. Okay. Next is the ionic or electrovalent bond. Ionic or electrovalent bond, that is from the Posel and Lewis treatment of the formation of ionic compound, that is would primarily depends upon, that is, the ease of formation of the positive and the negative from the respective neutral atoms. Then second is the arrangements of the positive and negative ions in the solid, that is the lattice of the crystalline compound. So the formation of the positive ions involve the ionization, that is the removal of the electrons from the neutral atom, that the negative ions involve the addition of the electrons to the neutral atom. For example, metal ion, that is metal gaseous atom gives, that is metal plus, that is oxidation, gas and 1 electron, that is this is ionization enthalpy. So we can write it ionization enthalpy for this first step. Then in halogen atom, like 1 electron gains, so here the X minus gas, here the electron gain enthalpy, and the net is M gas, that is M plus gas, and X minus gas gives Mx solid. So this is the electron gain enthalpy. Here the electron gain enthalpy is the enthalpy change, that is when a gas phase atom into its ground state gains an electron. So the electron gain enthalpy process may be exothermic or endothermic. So the ionization of the enthalpy, that is in the other hand, the always endothermic. Usually ionization, this is always endothermic. Okay, that is electron affinity is the negative of the energy charge accompanying the electron gain. Okay, here then obviously the ionic bond will be formed more easily between elements with comparatively low ionization enthalpies and elements with comparatively high negative values of electron gain enthalpy. See, most ionic compounds have the cation derived from the metallic element and anions from the non-metallic elements. See, the ammonium ion, that is NH4 plus. Ammonium ion here, and this is the exception because of the made up of two non-metallic elements. Okay, it forms a cation of a number of the ionic compounds. So the ionic compounds of the crystalline states consist of the ordinary three-dimensional arrangement, that is cations and anions held together by the Coulombic interaction energy. So these compounds crystalline in different crystal structures determined by the size of the atoms, that is size of the ions, their packing arrangements, and the other factors. For example, that is NaCl. For a cubic system, we can write it here, the cubic system. So this is the cube. NaCl means, for example, this unit cell you are going to learn in class 12. There we can see the detailed studies. Okay, see this type and this type. This type. See here in a sodium chloride, NaCl structure like this means sodium chloride. This is the chlorine atom, bigger atom size, and this is a sodium atom, so Na plus ion. Okay. So in ionic solid, the sum of the electrons gain enthalpy and ionization enthalpy may be positive, but still the crystal structure gets stabilized due to the energy released in the formation of the crystal lattice. Example, the ionization enthalpy for Na plus gas, that is sodium plus gas. Formation of the sodium gas, it is 495.8 kilojoule per mole. So this is the why the electron gain enthalpy for chlorine, the Cl gas, one electron gain gives what? Cl minus gas. Okay. So here the electron gain enthalpy, that is minus 348.7 kilojoule per mole. Okay. So this sum of the two means you will get, that is plus 495.8 minus 348.7, you will get it 147.1 kilojoule per mole. So this is the more that the compensated by the enthalpy of the lattice formation, that is sodium chloride enthalpy is 788 kilojoule per mole. Okay, therefore the energy is released, that process is more than the energy absorbed. Okay, then thus the quality measured of the stability of the ionic compound is provided by its the enthalpy of lattice formation and not simply by achieving octets of electron around the ionic species in the gaseous state. Okay, next is the lattice enthalpy. The lattice enthalpy of an ionic solid is defined as the energy required to completely separate one molecule of a solid ionic compound to gaseous constituent ion. Example, NaCl is 7, suppose plus 788 kilojoule per mole means, this means that is 788 kilojoule of the energy is required to separate 1 mole of solid of NaCl into the 1 mole of Na plus gaseous atom and the 1 mole of the Cl minus gas to the infinite distance. So this is the process involved both attractive forces between the ions of the opposite charge and the repulsive force between the ions like a charge. Okay, so the solid crystal being a 3D structure, it is not possible to calculate the lattice enthalpy directly from the interaction forces of attraction and repulsions only. Okay, then next is a bond parameter, we will discuss in next class. Thank you.